committee members at the emails here provided, hvacsystems@cibse.org or groups@cibse.org. And if you are not part of our HVAC systems group yet, we would really like to see you there. And please find our website on the CIBSE website there through Networks Group and HVAC Systems. So finally, we have a LinkedIn page under CIBSE HVAC Systems Group, where we like to publish our write-ups of the event. So please feel free to read, share and comment as you see fit. I'm now going to pass over to Tony Day, who's going to introduce you to our speakers. Please enjoy. Thank you.
Good evening. Thanks, Marianne, and welcome everyone to this event, an update on keeping buildings safe during the COVID pandemic. As we all know, this is the topic of the moment, and we've been hearing an awful lot about safety in buildings and transmission routes of COVID. And I think the numbers that we have on the line today kind of testify to how important people think this is. So we have some excellent speakers tonight. Chris Idden will be kicking us off. He's the chair of the CIBSE Natural Ventilation Group, and will be talking about transmission pathways in buildings. Clive Beggs, who's an emeritus professor from Leeds Beckett University. Clive will be talking today about humidity and humidity effects and COVID transmission, which is an area I think that's been probably underrepresented in most of the presentations I've certainly seen to date. David Black from FLACT Group will be putting his take and spin on the CIBSE COVID guidance, the ventilation guidance that's out there, and I think to hear a little bit more about some of his thoughts around that. Harry Williams from ACOM will be talking about mitigation strategies for COVID in buildings, and finally we'll hear some case studies about safe management from Sean Webber from Savills. So that's the lineup today, and at the end there'll be a Q&A session which will run at the end. So we'll hear all of the presentations, but do keep your questions coming in through the Q&A box, and then we'll field the questions at the end. So first, without further ado, I'd like to hand over to Chris Idden, who will kick off the proceedings. Thanks very much, Chris.
Thanks, Tony. Thanks for inviting me. I'm just trying to find where my slides are. There we are. Hopefully you can see those. Okay, so my name is Chris Idden. I'm currently the chair of the CIBSE Natural Ventilation Group, and during the summer I did some work with a group at Nottingham University and academics from some other university institutions looking at the transmission risk and the role of ventilation with regards to SARS-CoV-2 far-field transmission. Okay, so the SARS-CoV-2 is a virus, and like all viruses, they can't replicate by themselves. They need a host cell in which to infect, and in this case it infects human cells in the respiratory system, and that's where it hijacks the machinery within those cells to replicate itself, and in so doing it encapsulates itself in a little lipid envelope, and then will present itself to the mucous membrane, where it then exits the respiratory tract, and it becomes encapsulated there again within a respiratory droplet. Now these droplets can range in size from less than 1 micrometer through to 100 to 150 micrometers. And this little illustration just kind of demonstrates that in the exhale puff there's a high concentration of these droplets of a range of sizes, and the larger of those droplets will fall ballistically, land on surfaces, and then those surfaces might be touched by someone who then can pick up the virus and touch their respiratory tracts or the mucosal layer in the eyes or something and transfer the virus. That's thought to be quite a low route transmission route. The main route of transmission is through inhaling the virus. And you can imagine that at close proximity, where we've got this high concentration within the exhale puff, the chances of you inhaling an infective dose are quite high because the concentration of virus is high. But as we move further afield, then the virus becomes diluted within the room volume. And there are other dilution events, including ventilation, that will remove virus from that space. However, in poorly ventilated spaces for long periods of time, these smaller particles, so-called aerosols, will build up, and then there is a danger that susceptible people might inhale an infective dose. Another thing that's worth noting is that the amount of aerosols, these small particles that are expelled via respiratory activities, change depending on what that respiratory activity is. So, for example, talking can produce 5 times as many, and singing or loud vocalization can produce up to 30 times more aerosols. So the more aerosols, the more virus encapsulated viruses within those aerosols, and the greater the emission rate of virus into the space. The BBC picked up on this and did some nice graphics just before Christmas to remind people to ventilate their homes if they were gathering during the Christmas period. And we can see here again this cloud of aerosols close to the person, but these could build up within the space if it's poorly ventilated. One of the issues that we have with this particular disease is that people can be asymptomatic whilst they are emitting the virus. And this is a nice graphic from a paper from last year in the BMJ, which demonstrates that at the point of infection, it can be 5 days prior to any symptoms being exhibited. So this person's respiratory system can be expelling viruses, and you can see the viral load increases right up until the beginning and the start of those mild symptoms. And people might not even recognize these mild symptoms. So it's quite possible for people to be unaware that they are shedding viruses to be within a space. And it's also possible that people wouldn't realise that their neighbour within the space is shedding virus. So this is where the problem comes, that we've got an emission of virus, but we don't know when it is, we don't know who might be emitting it. And the more people in the space, the greater the risk that someone could be potentially shedding virus into the space. And again, the respiratory activity can increase the amount of aerosols. The other thing, from individual to individual, the viral load can vary by several orders of magnitude. So some people might release less than 1 genome copy per minute, whereas others could be releasing tens of thousands of genome copies per minute, which also makes it difficult to try and assess the risk. And so that's why this group, we looked at a simple mass balance model where we try to assume the gains and losses of virus into a space. So here we have, in this picture here, we have an infected individual emitting aerosols which contain virus, and there are removal mechanisms which can include room filtration, biological decay, which is the natural decay of the virus over time, or it could be UV systems which increase that decay. HVAC systems might recirculate these aerosols into other spaces. Ventilation can help remove aerosols from within the space. And there are other removal mechanisms, which we've got the ballistic deposition, because gravity still plays a part, even if the aerosols are relatively small. Over time, they will settle. And there's momentum-induced deposition. So air movement, airstream movements will cause these aerosols to hit surfaces, and they will become deposited on the surface, and eventually they will become unviable. So this just presents this as a mass balance. We've got gains and we have losses, which I've just described. The main gain that we can consider is emission from a person, because we can consider entry of virus from outside and via infiltration to be almost zero. So we can just assume that they are zero. We can assume that virus is already present in a space. Maybe an infected person has just left the space. That could be considered. And all the dilutions can be turned into an effective ventilation. So they can be turned into essentially an air change here and an air change per second. So we've got dilution via ventilation, surface deposition, biological decay and UVC denaturing, respiratory tract absorption, and filtration. And all these terms can be added together into one dilution factor, and then the steady state of virus genome copies within the space can be expressed as the emission rate divided by this dilution rate, and then that gives you a mechanism to try and establish how many viruses might be inhaled by a susceptible person. Of course, G ranges over several orders of magnitude, so whatever value we get will have a very high uncertainty factor. So the way to get around that, we must mention, of course, that even though we've got a steady state of viruses in the space, it's the concentration of viruses that are inhaled that is important. So the larger the space, the number of viruses will get divided by that space volume. So the room volume does have quite a say in terms of how much of a viral dose you're likely to get. So back to this idea of using a relative exposure index to try and cancel out the uncertainties within the emission rate. So here we take the number of genome copies that might be inhaled by a susceptible person and divide it through by a defined scenario. And we used a school classroom, a junior school classroom, because its space is pretty well defined, certainly for new schools anyway, in BB 103, I think it is. So a room volume would be typically 148, around about 150 metre cubed. The number of occupants might be 32. We know the breath rate of a child, and we assume a respiratory activity of 75% breathing, 25% talking to generate an emission rate. And that enables us to have a look at the effect of ventilation on this relative exposure risk. And we used 5 litres per second per person, just an arbitrary value because that's the lowest allowable rate for a naturally ventilated space, as being a relative exposure index of 1. And you can see as you increase the ventilation, we can decrease the exposure risk, which is what you would expect, but it's a diminishing law of returns. So there comes a point where, certainly in the winter time, is over-ventilation that actually, that slight reduction in risk creates an increase in kind of undesirable user behaviours. It can create cold conditions, and it's actually these areas here where we've got poor ventilation where the risk can grow quite dramatically, and that's the areas where we should start to consider. I'll just skip over that one because I wanted to show you that the relative exposure risk is a function not only of ventilation, it's also a function of the room volume and also the exposure time. So if we just take this little map here, this is a ventilation flow of 20 people at 10 litres per second per person. We've got time running along the x-axis, and on the y-axis we've got the volume of the space. And we can see in the smaller spaces, even with a long exposure time, even in a well-ventilated space, we start to increase our relative exposure risk, which means that using CO2 as a guidance can sometimes be problematic because we can have good levels of CO2, but we might have a high exposure risk if our exposure times are long. Likewise, we can have a poorly ventilated space at the bottom here. This is 1 litre per second per person. And in the larger volume spaces, actually the risk is quite low for short exposure times in comparison. So we've got to try and consider that it's not just ventilation as a removal. We've got the dilution of a room volume. We've got the decay, the viral decay, and that is influenced because that's an air change that's influenced by the volume of the space. So anything that affects the half-life of the virus can have a significant effect on the relative exposure risk as well. So in conclusion, increasing ventilation will decrease the far-field transmission risk. Far-field transmission events can still occur even in well-ventilated spaces, but we'd expect fewer far-field secondary transmission events in better ventilated spaces. It also means that we need to continue to reduce exposure, face coverings, social distancing, and hand hygiene, as well as our ventilation. So I just wanted to thank the co-authors of this work, and thank you for your time.
Thank you very much, Chris. As I say, there are a couple of questions on this coming in, but I think we'll, as I say, we'll leave those to the end. that's a really good way to get us going and to sort of tee us up for these transmission pathways, and the airborne one being the key. So our next speaker is Professor Clive Beggs from Leeds Beckett University. Now Clive is on the phone, and someone else is going to be taking us through the slides, so hopefully there will be this will be fully coordinated. So I'm going to pass over to Clive, who will be talking us through his presentation on humidity impacts.
Thank you, and thanks, Chris, for that excellent first presentation. Now, I'm a little bit hampered here because we had technical difficulties, but hopefully you'll be able to hear me and you'll be able to follow. So what I'll do when I get to the end of each bit, I'll just say next slide and check that we're on the right bit. So we're on the cover slide at the front, first one, and you'll see that I've called it the impact of psychometrics on aerosol transmission of SARS-CoV-2 virus in buildings. Really, it's about temperature and humidity, which we can encompass as psychometrics, which is the science of air-water mixtures. And we're looking at that and the impact of that on the transmission of the infection. I should say that the work I've done here is actually going to be published in the next week or two, because it's been accepted by the journal PAGA. So it will be coming out, so you can get it. It's an open access journal, and it's done by myself and Eldad Avital of Queen Mary's. Now, you probably know that, as Chris has just said, that SARS-CoV-2 or COVID-19 is actually a respiratory, caused by respiratory droplets. It's what we call a droplet-borne disease. And these droplets, as Chris has said, they range in size, and we're recommended to stay 2 meters away. And if you look at that, sorry, we're on the second slide here, by the way. My mistake. With that, and you should see the red line that indicates 2 meters from the source, and you can see that all the droplets really 100 microns diameter or greater fall around about 1 meter, 1.5 meters. So you're clear of those. But then you've got a whole load of smaller droplets, and they travel further. The very small droplets can travel and get caught up in the air currents. But also the larger droplets, say 50 microns, they can travel further past that point. And in fact, when people are speaking and coughing, around 85% of the droplets produced are actually less than that 100 microns starting size. Now, if we actually look at the evolution of the droplets, they're not, this is the next slide again, called evolution of droplets. So if we look at those droplets less than 100 microns, they actually never actually hit the ground. They evaporate rapidly, and they evaporate down to some size which we're not too sure. It's governed by the humidity in the room space, and also the kind of amount of proteins that are actually in the respiratory droplets. But various authors have done calculations and tried to estimate this. And our thinking is that a 100 micron particle will go down to about half the size, a 50 micron particle. So really the particles that kind of don't hit the ground are likely to end up as particles, aerosol particles that are less than 50 microns, some very small and some larger, which will float around the space. But the important thing to realize is that that 50 micron particle has a settling velocity of less than 0.1 of a meter per second. Why is that important? Well, because around each one of you, you have a thermal plume. You're warm. Each individual in a room is warm. We have a convection current passing over and up past our heads. So we're on the next slide, by the way, which is the one which is respiratory aerosols and thermal plumes. And we can see on the left-hand side this thermal plume above the head of the individual there. And you can see that the velocity at the peak velocities, they're around about 0.24 meters per second, which is far in excess of the 0.08 meters per second settling velocity for that size particle. So what happens is those particles get entrained into the convection currents and travel up into the room, and while they're widely distributed around the room space by the thermal convection currents that occur in the room. And then they can, when they hit a still patch, bit that's where the velocity drops, then they can fall out. And obviously the larger particles drop down quicker than the smaller particles, but even a 50 micron particle will still take about 11 minutes to settle, and it will fall through the breathing zone. So we have a complex next slide entitled Droplet and Aerosol Transmission. We have a complex picture emerging. We have near field transmission, which consists of large ballistic droplets that behave ballistically, or a cone of finer droplets that are actually expelled from the mouth during certainly coughing, but also during speaking. So if you're in that near zone, then you could get exposed because you're exposed to a high concentration of the virus, and that exposure will happen within seconds. Whereas when you're out of that zone, the small aerosol droplets, as I've said before, get into the air and move around, and then you can breathe them in. And obviously, the higher the concentration, the greater the risk. But that takes minutes to hours, that kind of infection. So duration is important. Now let's look at the viruses themselves. Next slide, influenza and A and SARS-CoV-2 viruses. Here we see the influenza virus, which is also a droplet-borne virus, and SARS-CoV-2. And the two have got many similarities. They're both enveloped RNA viruses, and they behave similarly in the way that they're transmitted, although SARS-CoV-2 is more infectious. Next slide, entitled Seasonality Enveloped Viruses. Now, the thing many scientists have noticed over the years is that there's variations there's a season for influenza. Indeed, there's a season for all envelope viruses. And this study here that was done some years ago in Edinburgh, it actually looks at where they peaked. And you can see that the influenza A virus peaks in winter and drops down in summer, just like the SARS-CoV-2 virus. In fact, all the envelope viruses RNA viruses behave very similarly. So you see this seasonality, and the question is why? Why do we see this seasonality? Especially because infections are thought to be contracted indoors. So this is what we were looking at. Now, I've got a great advantage over most of my colleagues who work in medicine and in biology, in so much that even though now I'm a biologist physiologist, and I work in medicine and have done for many years now. I used to be, when I first started working, I was an air conditioning engineer, design engineer, and I used to teach that at Leeds University, teach psychometrics. Unfortunately, biologists and medics don't get taught psychometrics, and so you find some real howlers, mistakes in their papers sometimes, and misconceptions. And probably the biggest misconception is to do with relative humidity. People do statistical analysis on relative humidity, but as you're probably well aware of, relative humidity is actually a ratio of the vapor pressure over the saturated pressure. And vapor pressure is very much linked to moisture content. So we go to the next slide. That was psychometric slide. Now we go to the next slide, which is RH cannot be considered in isolation. And exactly that, we cannot consider relative humidity in isolation. We must consider it in terms of the temperature. And I've seen numerous biological and medical papers where people have been dealing with situations and like the one I've described down here, and they see there's a temperature at 0 degrees and 90% RH, and then there's another condition at 20 degrees and 50% RH, and they say, the condition at 0 degrees is more humid than the condition at 20 degrees because the relative humidity is higher. But in fact, the air is a lot less humid. It's drier, much drier at that condition. And this leads to some erroneous conclusions. Next slide. This is a paper that was published just this year in a very, very prestigious journal. And it's a microbiology paper to do with a virology paper. And looking at the virus survivability on surfaces. And you can see there, they've done the stats using, sorry, this is the slide, by the way, which says relative humidity is misunderstood. My mistake. And what we see there is they've used RH as an independent variable. Well, it isn't an independent variable, it's a function of temperature. And this can end up in some very wrong conclusions. And you see the title is incredibly misleading with this paper. It says, increasing temperature and relative humidity accelerates inactivation of SARS-CoV-2 on surfaces. Well, if you think about it, at 0 degrees and 90% RH, which is quite a common condition in winter outside, certainly where I am in Leeds at the moment, it's like that outside. That's ideal for it. That's not reducing it or inactivating it. So these kind of statements can be very misleading. So what we did was we decided, next slide, which is said experimental studies. We looked for all the experiments that had been done on SARS-CoV-2, and they'd all been done actually in what we call a Goldberg drum that keeps the aerosols rotating in the air, and they're actually they can stay floating for hours on end. And we found 5 teams that had done experiments on SARS-CoV-2 at various humidities and temperatures, and that summed up to 21 experiments, and the papers are all listed here for you. Next slide, please. It says exponential viral decay. Now, the decay, when you put a virus in an aerosol or on a surface, what happens is you get an exponential decay. And that is governed by the formulas that's shown here. And that formula is an exponential decay, first order decay equation. And it's got a K term, that's the decay constant. And that decay, if the decay term is big, then the virus dies very quickly. If the K term is small, the virus persists for a long time. And that's the thing we looked at. So next slide, which says psychometric model of SARS-CoV-2 survival in aerosols. And in our paper, what we have done is we worked out all the psychometric values. We worked out the enthalpy, the specific enthalpy of the air, the vapor pressure, the saturated pressure, the specific volume, which is the inverse of density. And what we found was that this equation that we've got down here, you can see on here, where K equals, and we've got a linear combination of weights for specific enthalpy, vapor pressure, and specific volume, produced a very good fit. And within the range of the conditions, the psychometric conditions that we were working under, which covers the range that you'd find inside in buildings, we actually found that it produced a very good prediction of the K value and thus the half-life of the virus in aerosols. In fact, what we found was that this diagram shows the fit, and it had an R squared of 0.72, which is very good. And then using the equation of underneath that on the right-hand side, we can actually work out the half-life of the virus in an aerosol. And what we did was next slide saying K values in COVID-19. What we did was we worked out the K values over the pandemic period for the 2020 up to 25th of October, which is when we submitted the paper. And we did it for London, Paris, and Milan. And we worked out from hourly data, and we worked out the average mean half-lives. And you can see in the top diagram, they rise up dramatically from about April onwards. And the K value reaches its peak in August, meaning that the virus decays faster in August. And if you look at the COVID cases for the UK, France, and Italy, you can see it's almost the inverse of that. The lowest infections are actually at the bottom in August, and they're much lower than they were in March. In fact, here on this diagram, next diagram, which says outside air mean half-life of SARS-CoV-2 virus. If we look now, we see that the half-life in August when the number of cases was at its absolute minimum and everyone thought the virus had gone away, is about a 20th of what it was in March when it was raging. So there's a clear relationship. But of course, that's outside. We're inside. So if we look at the next slide, which is model predictions, you can see on this psychometric chart, if we take air in at, say, 0 degrees and 90% RH, at that condition, the virus doesn't decay in the aerosols. But if you heat the air up and don't humidify, you might end up with the kind of condition that I've had all day in my house here in Leeds, at about 21 degrees C and 30% RH. And you can see that the half-life is now 110 minutes. And in fact, if we were to go to a summer condition where we had no heating on and maybe it was warm and humid outside, so it was 25 degrees C inside, and 60% RH, the half-life would drop to 26 minutes, much, much lower. And you can see, next slide, half-life in a room space at 21 degrees C, it says. You can see that actually, for the same temperature in a room space, humidity is very important. We can get a 3-fold decrease if the air becomes dry, which is exactly what we have at the moment in the conditions outside. So that means the virus lasts for much longer in the air. In fact, I estimated, next slide, indoor virus half-life range. I estimated that if you took a poorly heated room, it could be about 18 degrees and 25% RH on a very cold, dry day outside. That would have a half-life of around 181 minutes. Whereas when the air is 25 and 60% humidity, that's only 26. That's a 7-fold decrease. So that basically means that any virus that is emitted in respiratory droplets in that building will be 7 times more. There's 7 times more of it in the winter than there is in the summer. So any aerosol that you inhale has a much higher concentration. Any aerosol that lands on a table or a surface that you touch has a much higher concentration, a much higher viral load. But in red at the bottom, it says we cannot be certain that this half-life contributes to the spread of COVID, or this change in half-life contributes to the spread of COVID in buildings. And we don't understand the mechanism. Let me explain. Next slide, where it says implications. Because other things go on. Because most of the droplets produced are actually less than 100 microns in size. In fact, when you're speaking, about 88% of them are. And this, as the air gets drier in winter, and in my room at the moment, the condition is 21 degrees C and 31% RH. So it's dry air. The aerosols produced evaporate much more rapidly. They become smaller. You get more smaller aerosols, and they stay in the air for longer. They float around in the air. So potentially the concentration that you could get in the air is greater. And of course, they've got a higher viral load because they're lasting for longer. So we've got a physical effect going on because of the humidity and a biological effect. Next slide. And in fact, there are other things going. So we've got differences between summer and winter. And we've got a table here. And at the top, we've got the first row compares the half-life. And as we've described, it's much longer in winter than in summer. The next one down describes the aerosol droplet size. They're smaller in winter than in summer, and they stay in the air for longer. So therefore, they're more likely to be breathed in. Also, if you go to the third row down, ventilation, we tend to have less ventilation in winter than in summer. We often recirculate the air, which makes the situation not very good at all. So basically, we're not flushing the particles out of the air as well. Fourth row down, our habits change. We spend more time indoors during the winter than we do in the summer. And finally, and very importantly, immunity. And I'm lumping a few things here, but basically we have more sunlight, more UVB light in the summer than the winter. So our vitamin D levels are higher. Also, the air is drier in the winter. So actually the whole of the nasal cavity dries out, and that may change the ability of the body to fight or to the immune system to defend against the aerosols. It might be that the aerosols stick much better to the receptors in the winter time than the summer. So these are all things that humidity makes a difference. I won't talk about the next slide, sorry. So we'll bypass the slide, which is COVID-19 transmission key issues, to go to the last one, which is conclusions. So the conclusion slide, there's clear evidence that COVID-19 is transmitted by respiratory aerosols that become airborne. It's possible very accurately to predict the expected half-life, certainly within the kind of conditions that you find in buildings, using a linear regression model and the psychometric qualities of the air. Thirdly, the virus, so this means that the virus survives for much longer in the dry, cool conditions. Fourthly, you get a lot more smaller particles in winter, so they stay around for much longer. But we still cannot say whether this is the thing that contributes to the increase of the virus, because we need to do epidemiological studies to show that. But I have to say, I think it is, but more work needs to be done in this important area. It's been overlooked, really. Thank you very much.
Thank you very much, Clive. That's really
Did you get it all, by the way?
Sorry?
Were you able to follow my rather bad instructions?
I think it all went very well. That was a great bit of teamwork, actually, and the slides coincide with what you were saying, so it's really good. Well done. It was really. It's very interesting. It's obviously stimulated a lot of interest in the Q&A, so we'll come back to that. But certainly highlights the importance of ventilation. It highlights the challenges of winter time in buildings, and the aspects of humidification in buildings is one that, as I think, as you say, has been possibly not discussed enough. So from the transmission of the virus, we now look more at perhaps the sort of technical services aspects of how these transmission pathways, and we're going to hear from David Black, Flaps Group, who will tell us his views on the guidance.
Thank you, Tony. Good evening, everybody. I'd just like to start with this quote I've taken from REVA guidance. For those of you who don't know, REVA are an umbrella organisation for every European version of CIBSE in the EU. There is currently no evidence of human infection caused by infectious aerosols distributed through the ventilation system air ducts. It says air ducts, but it should really say supply ducts. The risk is rated as very low. However, measures to reduce internal air leakage in ventilation systems can be taken. So what I'm going to talk about tonight is which AHUs are best for minimising transmission, what can be done to make these individual unit configurations safer, a little summary at the end, and then questions I think we'll leave till the end of everybody's presentations. So I would draw your attention, if you're not already familiar with it, to the CIBSE COVID-19 guidance, very comprehensive document, and I'm going to basically talk about the elements that are contained within the two sections that I've identified. I would also point everybody in the direction of the REVA guidance, similar document, perhaps slightly more detailed in some aspects, and it's available for free download from the REVA website. So there are a variety of air handling units. The first one I'm going to talk about this evening is runaround coils. They are obviously inherently safe in respect of any viral load that's generated in the space is exhausted to atmosphere without any possible configuration of or mixing of airstreams. And I'm going to introduce a new term to you, perhaps. It's exhaust air transfer ratio. That is defined in an EN standard, which is also a BS standard, and it's the level of carryover of extract air to the supply air. If a building is occupied and somebody has COVID within the building, it's obviously desirable that that air is not recirculated by the air handling unit. So in the case of a runaround coil unit, obviously the EATR is 0, no risk. Plate heat exchangers I've always considered to have completely separated air streams, but that's not actually quite the case. I've taken this from the Hovel Guide to Plate Heat Exchangers. it must be noted that plate heat exchangers are not 100% leak proof. So in respect of a plate heat exchanger, we couldn't describe it as no risk. We can supply it as define it as low risk. And why is that? EN 308, which is the EN standard for the testing of plate heat exchangers, or in fact any heat recovery system, allows an internal plate leakage of up to 3%. That is, there could potentially be 3% of the exhaust air being circulated into the supply air stream, assuming that the unit is working in accordance with the test conditions in EN 308. But that's not always the case. The pressure differential could be higher in reality, in which case the leakage rate could be higher in reality. However, there is a little bit of a fallback position. Eurovent, who certify a number of manufacturers, have a slightly higher criteria for acceptable leakage in cross-plate heat exchangers. So a Eurovent certified manufactured air handling unit, the plate can only leak by 0.5%. So if there is any degree of mitigation in a design going forward, I would advocate the use of a Eurovent certified manufacturer over a non-Eurovent certified manufacturer, because there's a greater guarantee that the plate will be leaking less than merely an EN 308 certified plate heat exchanger. And of course, any plate unit, any cross-plate heat exchanger unit that has a recirculation section is by its very definition a high risk, which is why the CIBSE advice is to deactivate recirculation sections to prevent recirculation of COVID material. So rotors, the initial advice from CIBSE was to turn off a rotor. And one of the principal objectives of my presentation this evening is just to put a little bit more detail onto leakage in air handling units with rotors, because they can be configured in different ways. This is a very unusual configuration of an air handling unit with a rotor, that is with both fans on the atmospheric side of the rotor. And I'll draw your attention here to a Eurovent document. Again, it's free to download. It's all about air leakages in air handling units. And for this configuration, Eurovent would say that the EATR is 0, as in there is no recirculation of exhaust air into the supply airstream. So this is inherently a no risk solution, but it does impact on the efficiency of the air handling unit. And hopefully when we're past the peak of the pandemic, there will be a focus then on running air handling units as efficiently as possible, because we will have some economic challenges going forward. This is another configuration. This is where both fans are on the system side of the rotor. And again, according to the REVA guidance and according to the Eurovent guidance, this causes very high EATRs. Up to 35% of the exhaust air could, in this configuration, be recirculated into the supply airstream. I've described that as a medium risk. It's probably medium to high. And a purge sector on a rotor doesn't work in this configuration. Again, a rotor unit with recirculation is inherently a high risk. And an air handling unit with the fans either side of the rotor is inherently low risk. According to Eurovent, the EATR with a purge sector is somewhere between 0 and 5%. Without a purge sector, somewhere between 3 to 7%. So the question is, what is a purge sector? A purge sector is a mechanical device that captures or projects a jet of air through the rotor from the clean airstream to the dirty airstream, and it attempts to blow off as many particles as is possible that are captured by the rotor and then direct them into the exhaust airstream. So the safest solution for a unit with a rotor would always be to specify a purge sector in addition to the rotor. And it's not a particularly expensive device. You can see from the diagram on the left, it's basically a mechanical notch. It's a little bit of tin, to put it in its crudest terms. So in addition to a purge sector, what else can we do? Again, this is REVA. REVA have produced an excellent document about limiting the internal air leakages across rotary heat exchangers. And in addition to a purge sector, what REVA say is balance the pressure differences between chambers P22 and P11, and that will eliminate a leakage by setting up the correct relation. So essentially, if we have an overpressure in section 22 of more than 20 pascals than is in section P11, we will cause any internal leakages within the unit to be going from the clean air stream to the dirty air stream. And for this particular configuration of fans, this can be done by regulating the exhaust damper, which is in perhaps an unusual position for a standard air handling unit in the UK. But in this configuration, we can then regulate the damper here to vary the pressure in this chamber and ensure that any leakage is up the face of the rotor from the clean to dirty airstream. So again, according to the REVA document, with pressure control, so with this throttling damper, less than 1% of the exhaust air is recirculated, and this then would go from being a very low risk into virtually no risk at all. And then we end up with a unit that has the best for overall efficiency, it has the smallest footprint, and it's the lowest cost, and it's as safe, if not safer, than a cross-plate heat exchanger unit. So that would be the normal direction of airstream without pressure control. That would be the direction of leakage across the face of the rotor with pressure control. We as a manufacturer have had this for 6 years now. There are other manufacturers who can offer some form of automatic pressure balancing or pressure control. So this isn't unique to Flat Group, but I would strongly advocate any specifications for units with rotors, that any specification going forward has not only a purge sector, but also some form of pressure balancing across the rotor. And for existing installations, there is a methodology within that REVA document to measure temperatures in various chambers within the air handling unit to arrive at an anticipated figure or a method of estimating the EATR, and then working out retrospectively whether it would be appropriate to add some form of throttling system pressure control for any units with rotors to minimize the amount of recirculation or to virtually eliminate it. So just a quick summary. If it's a unit with a rotor, this is the most recommended configuration according to REVA. That's with fans either side of the rotor. REVA also suggests that to properly operate the rotary heat exchanger, it should be fitted with a purge sector and correctly set up, in which case the leakage rates are very low, practically less than 2%. And in addition to the purge sector, not only REVA but CIBSE recommend some form of pressure balancing or throttling, and where properly configured, that reduces the EATR to less than 1%. But there are going to be configurations where it's impossible to limit the amount of recirculation. So that would be plate units with a recirculation section, rotor units with a recirculation section, and rotor units where both fans are on the system side of the rotor. And in those cases, if you want to put this unit back into operation, the only real practical way to prevent COVID material being recirculated by the air handling unit would be to add a UVC disinfection section. And that's in accordance with the REVA guidance. And for more details on UVC and other methodologies, I'll then hand you over to Harry. I'll stay online to take questions at the end. So thank you for your attention.
David, thank you very much. Excellent presentation. So we're now getting into the understanding of how these risks are being transmitted around buildings through the systems and how to mitigate that. So next we have Harry Williams from AECOM, who's going to talk to us about UVC technology and how we can use these technologies to help mitigate the risks. Harry.
Thank you very much, Tony. Could you just let me know that you can see my screen?
We can indeed. Well, I can.
Fantastic. Thank you very much and good evening. Today I will talk about the impact which UVC has on COVID-19 and explore some alternative technologies to reduce the transmission of respiratory viruses within indoor settings. Ultraviolet light is a component of the electromagnetic spectrum that falls in the region between visible light and X-rays. Ultraviolet light covers the wavelength range of 100 to 400 nanometers, where UVC light can be subdivided into 4 categories, as seen on the screen. The UV range of 200 to 280 nanometers can be used effectively for disinfection, and it will be my main area of focus for today when referring to UVC. Most natural UV light is generated by the sun, where 10% of sunlight is UV, and only about 3 to 4% of that UV light actually penetrates the atmosphere to reach Earth. There's no measurable UVC from the sun which reaches Earth, as it is absorbed by the atmosphere, and that's ideal, as exposure to UVC light is extremely dangerous for humans. As validated by multiple research studies, when biological organisms are exposed to UVC, it can kill or disable the growth of microorganisms such as bacteria, viruses, and other pathogens. That is true for COVID-19, where a sufficiently high exposure from UVC can inactivate and destroy the virus. UVC was previously used to combat the SARS virus, which was another type of coronavirus, and was used in the front line in China during the first wave of COVID-19 to disinfect buses, hospitals and trains, and is used extensively in the healthcare sector for disinfection today. UVC has been produced artificially for decades, and given that it's effective in the fight against COVID-19, there have been some fantastic advancements in this application, in the application of this technology. Today I'll explore 2 examples where UVC is used to reduce the transmission of COVID-19 and other respiratory viruses within indoor settings. The first product I will discuss today is UVC filters. As has been alluded to, HVAC systems can facilitate the circulation of respiratory viruses around buildings. UVC air filters have the ability to produce an extra layer of filtration and can reduce the spread of microorganisms within a building. As seen in the diagram, a UVC lamp is placed inside a duct system, parallel to the airflow, where the potentially contaminated air receives a high dosage of UVC light. The UVC filters are ideally placed downstream of any existing filters that may be present in an air handling unit, for example, so they can work in combination with them. The UVC filters do not require a pressure drop, meaning there's no extra power consumption needed for the fan to circulate the air. The UVC lamp does require a power supply and a small structure to hold the lamp in place. However, apart from that, there's very little impact on any initial base build design. The only added impact on a previous design is in relation to safety, and I'll touch on that later. Economically, the cost of a UVC filter is 20% the value of a HEPA filter, and research suggests that they produce a similar performance when filtering out microorganisms. There are a large number of products available, and finding one which operates safely and effectively is of paramount importance. Today, I'll focus on one product produced by Flact, which has the ability to disinfect more than 90% of airborne viruses and bacteria. The effectiveness of UVC against respiratory viruses is dependent on the dosage which the air receives. The factors which affect the dosage received are reflection, humidity, section dimensions, and temperature. Flact have designed the UVC chamber to optimize these factors to ensure that the air receives a sufficiently high dose of UVC to eradicate more than 90% of viruses, and that includes COVID-19. And not only does the device operate effectively, it does so safely with the inclusion of UVC resistant viewing windows, so that will allow for the device to be monitored safely. There are door contact switches, so that automatically turns off the UVC lamps when access door is open, and that allows for maintenance of the device to be carried out safely. And there are inclusion of light traps, so that prevents any leakage of UVC onto components and areas underneath the device where people may gather, so it doesn't harm them. So this is one alternative solution to combating the transmission of COVID-19. And should you wish to inquire further on the products, I'm sure David would happily supply you with the relevant information. The second product I will discuss today is our standalone air purification units, which are an in-room solution. The units can be placed on any surface in a room, on a wall or a ceiling, and require only a power supply to operate. There are many units available, however the general configuration is of a fan on one end which sucks in contaminated air via an air or a carbon filter, sometimes both. Having been filtered, the air then travels into the enclosed UVC light chamber, which contains some sort of UV light arrangement. The UVC radiation eliminates any microscopic particles in the air which could not be caught in the filters. Once the air is disinfected safely, it's then recirculated into the room as clean air. There's no risk of harmful radiation exposure to people when the device is in operation, as the UVC disinfection process takes place within the enclosed chamber. And the device allows for the immediate eradication of harmful respiratory particles while having minimal impact on the base build design. It's the case again here that there are many great products available on the market. When conducting our own research at AECOM, I produced a technical report which assessed the effectiveness of different air purification units for a particular project that we were working on at the time. So for our own specification on the project we were working on, one device appeared to be the most suitable, and it was known as the Luxibel B-Air V2 device. And that was for two reasons really. Firstly, it had an impressive operating system. It contained 2 filters, and that was combined with a powerful UVC light configuration. So exposure from that ensured that there'd be no harmful microorganisms left in the air. And secondly, there was validation that the device was effective in combating against harmful respiratory infections. And that was really important to us because there's endless unknowns of COVID-19, and validation that the product worked effectively against the respiratory virus was of huge importance. Luxibel was one of the first manufacturers to conduct a scientific research paper to establish the effectiveness of their device against respiratory viruses. The results of the experiment can be seen on the screen, concluding that the Luxibel device was highly effective at eradicating microorganisms in a room, and importantly, ones with a similar composition to that of COVID-19. And this was validated by 2 separate institutions. It showed that one unit can purify an area of 25 meters squared, and that correlates to a volume of 55 meters cubed. And as the results on the screen show, 2 devices were able to safely maintain a volume of 100 meters cubed, and that eradicated 98% of all microorganisms in that space. Another interesting point that was flagged up in the research paper was that the device was more effective in a mid-air disinfection configuration. And that's because the device worked with the natural air circulation within the room. Any harmful microorganisms propelled outwards by guests will be sucked upwards, neutralized, and blown back into the room. The arrangement can be this sort of arrangement can be adopted in areas of particularly high congestion, such as concert halls or lecture theatres of the like. So this standalone air purifier is one of many available on the market, and I hope this has sparked your interest for designs in the future. Thank you for listening, and if you have any questions, I'll happily address them at the end. Excellent,
thank you, Harry. That's a very interesting run. Again, this is probably an under-discussed area, so it's really good to see presentations on the effectiveness of these devices. So we now want to move into a case study. So Sean Webber from Savills is going to talk to us about managing COVID in the working environment, and I think this is what we all want to know: how to do it well. So Sean, over to you.
Thanks. I'll try my best. So I'm Sean Webber. I'm from Savills. I'm an engineering and property manager, and currently I manage 70 Mark Lane, which is situated just outside of Fenchurch Street Station. The building achieved practical completion in December 2014. It's 170,000 square feet, over 15 floors, with floor plates ranging from 14,000 square feet to 5,000 square feet. We also have 4 retail units that have 3 out of 4 have stayed closed throughout the whole pandemic, but 1 has remained open, so that's provided its own challenges. And we also have a winter garden space, which is really nice, that we have offered to occupiers who have been in to use for open air meetings upon request. It's just a step away from Fenchurch Street Station, and it's a very short walk from the Lloyd's building and the insurance district. The building is managed by Savills on behalf of Knight Frank Investment Management. There's a few pictures of the building, so you can will get familiar with it. As you arrive at 70 Mark Lane, you are greeted by a PPE disposal bin and a battery-operated sanitizer station. We have also installed a welcome mat informing you that you're in a socially distanced safe zone. When looking at the queuing system for the free reception desk, we decided against stanchions, as this makes the reception feel very crowded. We sat back and we brainstormed and opted to go with floor mats, eliminating the risk of tripping and touch contact you could have from a stanchion. So there's a view of if you were to enter the building. As you can see, the queuing mats there replace the instead of stanchions. It can really make the area feel so crowded. We've also installed a 16mm Perspex cough screen that carries the length of the reception desk. This has been glued so it can be removed at ease and stored for reuse when no longer required. Managing the lifts, the existing lifts at 70 Mark Lane, allowing full occupancy and working to a full building and operating at a mix of peak traffic, can handle 6.5% of the building population in a 5-minute period. This equates to 102 people transported safely every 5 minutes. Up to 549 people can occupy the building with no impact to lift services, even when the cars are limited to 4 people. With the lift limits to 4 passengers, up to 488 people can occupy without particular need to ration their access to lifts. A higher population can be accommodated, which will take longer to fill and empty the building at either end of the day. At these higher number occupying times, the demand for lifts is used by rationing services to lifts. The way we've done this is we've made sure that we encourage staircase use throughout the building. Ration lift use applies in the down direction, as the main lobby is controlled by the building management. The occupiers are advised to utilise the staircases for short journeys within the building. The lifts have been modified to assign no more than 4 passengers to a lift. This is readily achievable in the Compass system, and Otis have carried this out under instruction. This now means that the lift system will no longer accept any more calls once 4 calls have been already accepted by the main group controller. Additional measures we have taken, we've installed hand sanitizer stations in all lift lobbies. We have increased the cleaning regime on surfaces in lifts and lift landings. We advise passengers to ensure they wash their hands thoroughly following the use of lifts and escalators. We encourage the use of stairs for short travel to floors and especially short interfloor travel. We have alternated the east and west staircases, alternating the staircase direction throughout the day to assist with peak flows. We provide additional security marshals for peak times to make sure that no more than 4 occupiers can enter a lift at any one time. We advise face coverings are to be worn in the lift and lift lobby areas, and we have instructed electrostatic fogging on all landlord areas. The east staircase is used by the occupiers who wish to enter the building and use the stairs rather than the lifts. The east staircase is located at the rear of the premises, and access can be obtained by walking through the reception barriers and into the goods lift corridor. The west staircase will be used as an exit staircase for occupiers wishing to exit the building via the stairs instead of the lifts. The staircase leads to the Mark Lane side of the building. The west staircase fire exit will be opened and manned during the lunch hour 12 to 1 to allow a smooth exit and avoid congestion in the main reception area. This exit will also be manned from 4 to 6 to manage occupiers departing for the evening. We found just before the second lockdown, the building was back to around 1,200 people, and we found that this really did work well, and we found a lot more occupiers now do use the stairs to fresh air. At 70 Mark Lane, we have an occupation density of 1 person per 8 square metres, so we're very lucky that we can practice social distancing even at a maximum capacity. As this is the case, we provide 12 litres per second per person, plus 10% based on the 1 person per 8 metres squared. We keep air moving through the building. The supply and extract systems act as a natural diluter for any contaminants within. The supply air adding fresh, uncontaminated air, and the extract moving the stale, dirty air forward. We keep mechanical ventilation systems operating. We increase the run times to 24/7 and fresh air content to 100%. We have turned our thermal wheels off, so we have no recirculated air. And we have reviewed our system operation on all plant to check it is properly balanced, taking into account any changes in occupancy or space utilisation. This shows that we are achieving uniform air distribution throughout the areas supplied. So what can you do for any of you on the call that look after buildings. You can consider operating your ventilation systems to obtain maximum air change rates, making sure this is relative to the space and occupancy. You could run your air system 24/7 to the maximum benefit. You could choose to lower these rates but not switch off when there are fewer occupiers in the building, or use it in a secondary option to extend the current operation times of your ventilation system so it starts 2 hours earlier than normal and finishes 2 hours later. At night and weekends, I would advise not to switch ventilation off, but to run the systems at lower speeds. These options aim to provide the maximum amount of fresh air to your occupiers while removing any potential virus particles that have been transmitted within your building. Make sure your systems are set up correctly and utilise your engineering team's time. And just be aware that any of these come with a additional cost, maintenance and environmental impact. The toilets and drainage systems, although still not fully established, there are a number of simple measures you could take to control possible fecal transmission of COVID-19. These will also prove more effective for other viruses too, such as the norovirus. These could include flushing toilets with the lid closed, thereby reducing droplet plumes being created, therefore minimising any fecal transmission of virus particles. At 70 Mark Lane, we have 10 air changes per hour per cubicle. Obviously, it's all relative on the size of the cubicles and the size of the bathroom. Keep your toilet extract system maintained and operational, and consider bypassing any controls on your extract system and operating them continuously during occupation of the building. Try to maintain negative air pressure in the toilets. This keeps smells away as well as any generated contaminants out of adjacent areas such as toilet lobbies. Keep sanitary plumbing systems well maintained and preserve water seals, for example, by stopping any drain traps drying out and emitting bad odours. Actively promote good hygiene practices, especially hand washing using posters. So these are just some results from 70 Mark Lane, one of our last audits. The 70 Mark Lane carbon dioxide levels were close to or within the ideal band of 600 to 800 ppm. CO2 levels should be maintained below 1000 ppm. Carbon monoxide levels were negligible and significantly below the Health and Safety Executive Workplace Exposure Limit of 8.7 ppm. Nitrous oxide 2 levels were within the guideline limits as specified by WHO guidelines for indoor air quality, selected pollutants 2010. NO2 levels were found to be 38.25, which is the lowest limit of detection. TVOC levels were consistently within the boundary stated within the wellbeing standards, and TVOCs were generally very stable, showing there was no adverse side effects from any VOC emissions in these areas. The thermal wheels within the HUs have been switched off, which I've already touched on, to avoid air recirculation within the areas supplied. Only fresh air should be provided to floors to reduce the likelihood of any coronavirus transmission in the office spaces. So cleaning and hygiene. Effective cleaning and hygiene is another key thing to COVID-19 security. Reducing the potential for airborne transmission of the virus through good hygiene practices will again help maintain air quality. This could include, we encourage staff to adopt good hygiene practices at all times and back this up with poster and other campaigns. At 70 Mark Lane, we have utilised our ECN screens and have shared information with occupier marketing teams and hold regular toolbox talks with our service partners. We have amended the cleaning regimes to target the most effective interventions, more regularly sanitising touch surfaces such as handles, lift buttons. And we've better spent, which is much better than using our time vacuuming. We clean, sanitise desks regularly and use communal phones and equipment in touchdown areas or hot desks where all staff have antibacterial wipes on each desk. We make sure consumable soap, hand sanitisers and toilet rolls are readily available and accessible, and we regularly remove waste and check areas such as washrooms and kitchens regularly. Communication. So keep conversations up with your site teams and your occupiers. Keep everything centralised and accessible in case you fall ill. Keep on top of your crisis communication strategy, business continuity plan, and make sure all essential logbooks are always up to date. Make sure all your stat compliance is current, such as fire logbooks, water treatment logbooks. Keep communications personalised but to the point. For example, at the start of February, we issued each occupier with a clip-on sanitiser. Keep showing your occupiers the latest building enhancements on the market, such as contactless security exit control. It's not just about keeping the landlord area safe, it's also about keeping their internal offices safe as well. We've built good relationships with the Hackney Food Bank during this pandemic, making sure that any food that's surplus to requirements goes to them to assist others. We've donated sanitary products to a local women's refuge, helping others in need. We've also taken part in charity events such as the Football Shirt Friday and Xmas Jumper Day, as we found both events were great for staff morale. Thanks a lot. Cheers.
Sean, great, thank you very much. We're going to move to questions now, I think, but I'd like to start with a question to Sean, because I think what we heard in that great presentation there, you know, there are a wide range of measures that you can adopt to operate a building safely, and I think you've taken us through very comprehensively just how much effort has to go in to that. But one thing that jumped out at me was you switched the thermal wheels off and to maximise the ventilation rate. I think the importance of ventilation rate has been made over and over again. So that message, I think, has got home. But have you found switching the thermal wheels off, and maybe that you and David Black might have different views on this, but has that affected the way that the building has operated? Certainly, has the energy consumption gone up noticeably? Presumably it's bound to, or have there been incidences of people saying they're not comfortable in that environment because the heat recovery is off?
Well, due to other energy stuff, for example, lighting and power is being used at a minimal rate at the moment. So we've not really noticed an enhancement in energy usage, and we've not actually got smart metering to be able to monitor the exact consumption from that area. But it was actually pointed out on from our RPS audit that we should switch them off. So we were advised to turn them off by our air quality auditor. So that was following their instruction. So and because it was instructed in the audit, we carried it out.
I think that's interesting. It's just interesting to note, because the guidance has now moved on from the original guidance that said switch off, and now it's well, you should certainly keep the thermal wheels on if the configuration is correct. And I don't know if David, you wanted to have a comment on that.
Yeah, I mean, the purpose of what I was trying to show was that there are different configurations of air handling units with rotors with different fan positions, and they carry significantly different risks. The vast majority of air handling units supplied in the UK actually have the fans either side of the rotor and are inherently quite low risk, but that wouldn't stop the remedial action of pressure control being added to those units to minimise the risk further. And an audit of the configuration of an air handling unit with a rotor is to me the desirable course of action. It may well be that the unit is inherently safe and could safely be turned back on, but it may be inherently unsafe if both fans were on the system side of the rotor, and the best course of action there would be to either replace it or fit it with a UVC section. Okay, thanks. So what I'm going to try and do, there are a number of questions, so see how many we can squeeze in. So what I'm going to do is carry on that theme of thermal wheels just for the moment for you, David, and put a couple of questions, group a couple of questions. So there's one question: can thermal wheels be used for heat recovery? This is from Jason. And air handling units used in clinical areas, especially where there's exposure to COVID patients. And then perhaps, so coupled to that, in terms of what are the practicalities, if you, just assuming you can use them in some environments, maybe better than others, but how do you do this rebalancing, particularly this rebalancing between P11 and P22? That's a question from Andy. So there's a practical issue. So A, can they be used in environments with COVID? B, how do you actually set them up in practice?
There's nothing in HTM that prevents the use of air handling units with thermal wheels in hospital applications. I wouldn't suggest a thermal wheel for an operating theatre, for example, or in the treatment of a COVID ward or an isolation suite. Isolation suites would be dedicated supply and extract systems anyway. For other areas of a hospital, I would be comfortable with that, and they are used frequently right the way across Europe. And there's still no measured case of an air handling unit with a rotor causing the onward transmission of COVID. In respect of the pressure balancing, it doesn't have to be at the air handling unit. A system that regulated a exhaust damper in the ductwork, if it was correctly configured by a knowledgeable BMS engineer, could work equally as well as doing it at the air handling unit. We have the benefit of, we've manufactured rotors for many years. We've always understood the risk of leakage within an air handling unit with a rotor. And when we were upgrading our controls in 2014, we took the decision to include a pressure balancing bit of software such that we could always offer this system with our integrated controls. So we have a high degree of knowledge in the application of this. But like I say, it wouldn't stop a competent and knowledgeable engineer from being able to do this system in the ductwork if required.
Okay. Excellent.
And sorry, Tony, to interrupt. It's merely a question of measuring the pressure differential between the two chambers by means of a differential pressure sensor, and then regulating a damper to increase the exhaust system resistance to create that positive pressure of 20 pascals.
And there's another question from Colin Goodwin. In throttling of the inlet extract damper, this in turn will reduce the extract ventilation rate, so may reduce the air change rate by a disproportionate amount. Is that an issue?
It depends on how you configure it. So our controls are such that the fan is ramped up as the throttling pressure increases to maintain the correct airflow from the exhaust fan. And we always dimension the exhaust fan to account for the throttling pressure. So we can make the calculation of what the worst case throttling pressure would be and dimension the extract fan accordingly. And then it will always deliver the required volume flow.
All right, thanks. So I'm going to change tack a little here. George Vlachos is asking, do we have data on UV disinfection rates against airflow passing through equipment? So that's a question for Harry.
Hi. Yes, there is. I don't have that to hand just now, but there's obviously different parameters that affect the intensity to which is received by the UVC bit of equipment. David, do you have any more insights onto that with the work that you've been doing in Collect?
There is an industry Bible for the UVC, and the author is a guy called Kowalski, and it's fairly easy to find by searching the internet. And in the Kowalski guide, there is a table of power ratings for multiple different viruses and bacteria, of which coronavirus is one. The coronavirus that's in that particular table is the original SARS virus, but there is every evidence to suggest that COVID-19 reacts to the same level of power delivered by the UVC that the SARS did. And then essentially you have to make a calculation to deliver that amount of lamp power to the airstream with the correct contact time.
So I think that there are similar sort of questions about information. Are there standards on UVC resistant viewing windows? What about shadowing and residence time for single pass systems? So there are a range of these kind of questions, and we probably can't do that in detail here. So can we point people at where the best information can be obtained on some of this?
Yeah, I mean, I strongly recommend the Kowalski guide because it does go into a lot of detail about the safety measures that you need to take for an Airstream UVC system, including the correct specification for viewing windows, contact switches to prevent access to a UV section when the lamps are on, etc. Kowalski is a very good guide for that.
Excellent. And there are a couple of questions really about, are these systems applicable only for new installations, or can they be retrofitted easily? So
given the amount of space that we're given by architects to put mechanical services equipment in easily, well, it would vary from
from building to building in terms of a retrofit. They can be fitted into the ductwork. The length of the UV section is dependent on the velocity. So the higher the velocity in the ductwork, the more difficult it would be to fit into the system. But yes, it can be retrofitted to existing systems.
And secondly to that, the in-room solution that I referred to, which was the standalone UV air purification units, they are fantastic because they can be put anywhere in the room. So yes, they could be added to existing designs. And as I mentioned, they have very little impact on the power that they require. All they need is a power supply to operate. So yes, they could be put into existing designs.
So yes, so moving on, I'm going to change tack again. So Abigail Dombey asks Clive, do you have any idea whether the half-life of the B117 variant will be any different from the original COVID virus?
The answer is no, because we don't know what's going on there, but I suspect it's very similar actually. I suspect they're all very similar, the coronaviruses. It's to do with the actual structure of the virus, and I suspect what's happening here is the relationship between the phospholipid bilayer that Chris mentioned when he did his talk. Our phospholipid bilayer is actually taken from human cells when they bud up, when the virus buds off, and it will have it's actually hydrophilic on the outside of that, and there will be moisture, some water of some nature inside between that and the capsid of the virus, and also you have the microenvironment outside where the droplet is, and that's evaporating. And I suspect that what's happening there is you're getting changes in the chemical structure and the osmotic characteristics of that. And I suspect that that is because we know that the COVID is behaving similarly to, with respect to humidity, to influenza A, which is also an RNA envelope virus. So I suspect that all the strains of the SARS-CoV-2 virus will behave in a similar manner. This is not really a genetics thing. This is more a kind of structural biology thing to do with the envelope.
Okay. There's a question here really again about the transmission through an HVAC system. Does it depend on how well maintained the system is? So if the fan is operating correctly, are the filters need changing, etc. I mean, I think it would be a clearly obvious answer would be let's maintain our systems as well as possible. But is there any evidence that transmission might be increased? Chris, I wonder if you want to talk a little bit about transmission through ducts.
Okay. Well, I think the important thing to remember is that as long as some outside air has been brought in, that there is some dilution happening. So as long as there's some form of dilution happening, then that would be okay. I don't believe we've seen virus transmitting via ducts from one room to another and causing secondary transmission. One of the reasons is that if you've got an infector in a space, it is that space where the vast majority of the virus is going to be, the highest viral concentration. Once it's moved to another room, it gets diluted again by the room volume and also by any outside air that's been brought into that space as well. With regards to maintaining, I don't think I've got anything else to add other than what you said, Tony. I can't see how all maintenance is going to kind of increase that unless it's reducing the amount of outside air that's been brought in.
Okay, excellent, thanks. Of course, Clive, yes.
Could I add something to that, Chris? I've got to give a clinical epidemiological answer to that. There is no evidence epidemiologically for this particular virus is transmitted by recirculation through ducts. But there is lots of evidence for tuberculosis being transmitted via ducts. And the same things that Chris has described there, the tuberculosis bacilli are diluted just the same way. I know it's a different disease and it is different in its way, but there was a case certainly in a US warship called the Richard E. Byrd back in I think it was the 1970s. I think it was published in about 1980 this was, where one rating on undiagnosed with TB managed to infect, and it was tied down to the recirculation system on the boat. I think it was 147 other people, or 145 other people. So there is clear evidence of it going on with other diseases, respiratory diseases. So I wouldn't myself rule it out, but it is very difficult to do the epidemiology to actually demonstrate it. But of course, it is different to tuberculosis in some ways. So Chris may well be right on that.
Clive, I'm just going to stick with you around the humidity issue. There's a question here about, is it possible the high humidity in a tropical climate, for example Malaysia, turns out to be an advantage? But there are related questions to whether the drying out of droplets in low humidity is an issue and they stay airborne for longer. So I mean, this is obviously a complex issue. We see in some tropical areas there are high infection rates. How important is this humidity issue?
I think it's extremely important, and I think we're only scratching the surface. You've got to realise that there's an awful lot of factors going on here that into the transmission. So we're talking here about aerosols, and we're talking about transmission via aerosols. So certainly Malaysia and subtropical sub-Saharan Africa seems to have less incidence of the disease, and it tends to be more in South Africa, which is colder, and generally the hotter and more humid places tend to have it less. But of course, then we have South America, we have Brazil, which is hot and humid. So we can't really fully understand this. And of course, it may be down to people, if you don't social distance and you are very tactile and you know, effectively, I'm not saying everybody's kissing each other, but if everyone's really close up and personal, then it will be transmitted by other routes. So you've got to take this into account with all the other factors. But all the evidence is suggesting there is a seasonal approach, and that somehow, in some way, this affects the transmission of the virus.
Yeah. Thanks. Now, there's a few questions here around bipolar ionization. So is there any experience in the team about with bipolar ionization and control pathogens?
I've published various papers on this, not so much on the bipolar, although I've tested out bipolar before now. Yeah, I think it's got a lot of potential, but unfortunately it's not really being tested out properly on certainly on SARS-CoV-2, as far as I know. And again, we don't know, it will deposit the virus onto surfaces, and that may make the thing worse because we may not have more contact from fomites, or it may make it better, and we just need to understand more about it, really.
Okay, thank you. Now we have very many questions. There are more coming in all the time, and we've only got a couple of minutes left. There is a question: is it considered safe to operate fan coil and VRV systems? Obviously, fan coil units will be circulating air within a space. And before I pass that one over, of course, the classic example, and this goes back to stuff that Chris was saying earlier, the classic example of air conditioning systems or an air handling system that was seen to transmit or seen to be part of a sort of transmission is the Guangzhou restaurant, which was a fan coil unit in a space, in an otherwise unventilated space, and it seemed to be a direct transmission pathway of viral load being picked up in that airstream and passed to adjacent tables. So it didn't go through ducts. So so fan coils and VRV systems. Chris, do you have any comment on that?
I think the CIBSE guidance again on that is providing there's an outside supply of air into that space, then the risk is not necessarily any higher. The mixing might actually help in terms of diluting any virus within the space. However, like you mentioned in the Guangzhou episode, here the jet streams might be moving larger droplets further, and those larger droplets can have a higher viral load. So that could be another factor to consider if someone is downstream of a jet stream for from someone who is infected. That could be problematic. I don't know if Clive's got some further info on that.
Yeah, I've been thinking about this. I mean, earlier on this year, I kind of published a paper which was really criticising the WHO stance at the time. This is around about April, where they were saying there's no airborne transmission. And I pointed to this issue in the restaurants, where they very neatly sidestepped the comment out airborne and called it droplets being moved by the air. You know, the problem was that the definition that we have of airborne is anything that's under maybe 5-10 microns that goes deep into the alveoli, like TB, which is a clinical definition, not an engineering definition. And the one thing we certainly can say from I can't pronounce the name of the place very well, but the restaurant in China, that outbreak was that viral particles were moving in respiratory droplets, aerosol droplets, through the air. So they were, engineering-wise, airborne, maybe for a short period of time. And that makes me think that it's really important to look at maybe particles that can be moved by air currents that are maybe of the order of 100 microns down to maybe 30, 40 microns, that kind of in-between zone that tends not to be looked at, because they can carry a very large viral load and they can be inhaled. So and they are likely to impact actually in the nasal cavity. They'll actually impact on the receptors at the top. That's where you smell first. And I think that could be a very good clue about the major route of transmission. These larger aerosols seem to me to be quite important. How that fits with the humidity thing, where we tend to get smaller aerosols, I do not know. There's lots of unknowns here, but I certainly think it's important to look at. So I agree with Chris completely. We need ventilation, but I wouldn't want to be stuck in a loop in that restaurant where the air was kind of almost caught in a cell, and it was just a concentration going to the next table, if you know what I mean. Chris, you got anything to add to that?
No, I think you explained it well. I think from your slide with that cone, if you can imagine that cone of high concentration of larger droplets and smaller droplets being spread a bit further because the air movement is greater. That's how I kind of imagine that.
I think one of the things that we really need to get over is that this is actually a dose-related disease. I don't think it's caused by just one particle. The greater the concentration, either from the amount of time that you spend in the space and breathe in more particles, or the amount of concentration in the air that you're bringing in, is really important. So if you get a large dose, if you're close to someone, you get a lot of aerosols, you've taken a large dose, then some of them are going to hit the target and you're going to get ill. That's my way of looking at it.
Absolutely. When they land on the mucosal membrane, they've got to, well, first of all, when you breathe in, most of them you'll probably breathe back out again, but some might land onto your mucosal membrane, and then they've got to overcome that, bind to your ACE receptor, and then infect you. So I think for the SARS virus, I think you needed an infective dose was about 400 genome copies.
Yes, yeah, but that's not actually the particles. Sorry, I mean the aerosol particles. I mean, it's a bit of a guessing game on that one.
Absolutely.
So there are so.
Could I just chip in a second there, Tony? Just things to. There was a very similar super spreading event to the Guangzhou restaurant in actually in South Korea in a Starbucks, and again it was associated with a ceiling mounted air conditioning cassette, causing high velocities across people sat inside the building. So it definitely replicated this situation from China. Again, I without wishing to blow the trumpet of REVA over CIBSE, REVA have produced a specific document about the operation of fan coils in occupied spaces, and that is available for free download from the REVA website.
Right, thank you. So look, we've had a lot of questions. This is and I know there's a large audience out there, and I think this has stimulated obviously a great deal of interest. I'm afraid we don't have time to put all of the questions to all of the speakers. However, we've got these questions and we can try and get responses offline if possible. Let's see how we do that. But hopefully we've covered a lot of ground, and we've answered some of your main concerns about the transmission of this nasty disease in buildings, and how we as building services engineers are responding to that. And I think what we've heard tonight, it is complex. We don't know all of the answers, but there are some very simple messages. Good ventilation is absolutely paramount. We're now hearing the importance perhaps of humidification. So should we be switching thermal wheels off that have latent heat recovery, and as well there might be an advantage to that, although it won't necessarily lift it to the levels that that Clive was showing can improve that, decrease that half-life. But so there's a whole range of important issues here about air distribution, about fresh air, about how the virus is transmitted within spaces. So I hope that we've all learned something really interesting here. I'd like to thank all our speakers: Chris Hidden, Clive Beggs, David Black, Harry Williams, and Sean Webber. I think there's a really interesting range of talks. And if you do have questions, do fire them into the HVAC group. Sign up to be a member of the HVAC group, and find out what other interesting events that we have coming up. I'm going to ask Mary Ann if she has any last comments to say, but I'd like to thank everybody for joining us on here. Thanks to all the speakers, and we'll hopefully see you next time.
Thanks for that, Tony. Yeah, the only thing that I wanted to add that I probably should have mentioned at the beginning is CPD certificates will be sent out if you applied through Eventbrite, so they will be winging their way over to you shortly. But I'd like to say thank you as well to all our presenters and to Tony, and to all our listeners as well, and we hope to see you again at the next event. Thank you very much.
Yeah.